Okay, so welcome everyone. Let me first thank you for joining this Capella webinar. I'm Rochet and I'm working for Build and I will be your moderator today. It's time to welcome our speaker. Pablo Lopez Negro is Chief Innovation Officer at Anzen Engineering and the product owner of the ATICA model-based safety analysis tool. He is involved in the aerospace industry for nearly 10 years. Started as guidance, navigation, and control engineer, where we first discovered model-based and model-driven approaches. Then he evolved towards a system engineering position before becoming MBSE specialist and designer and developer of MBSE frameworks in Anzen. So welcome, Pablo. Thanks to be with us. And please tell us more about ATICA.
Yeah, thank you very much, Samuel. Thank you very much, Obeo, for the opportunity of being here today. I have to say that I'm very proud of being a presenter. I have seen dozens of Capella webinars in the last couple of years, but for the first time, I'm at the other side of the world, let's say. And yeah, so happy to be here. Just 1 minute, I will share my screen. Okay, I think it's working now. Samuel, can you confirm?
Yeah, I confirm.
Okay. Yeah, so sorry for the slide problem. Okay, so before starting, yeah, again, thank you very much, everybody, for joining today. I will be talking about ATICA. ATICA is the model-based safety analysis framework that we are developing in Anzen Engineering. It's a model-based framework that is fully compatible with Capella, and yeah, I'm just looking forward to show you around this tool and yeah, get feedback from the community and hopefully get all of you to enjoy the next couple of minutes, well, a little bit more than a couple of minutes, but yeah, the next, let's say, half an hour roughly that this presentation will last. So before starting, what is Anzen and what are we doing? So Anzen stands for safety in Japanese, which is a pretty convenient name for a company that is specialized in system safety and reliability engineering. We started in Madrid, Spain in 2019. First as providers of service support mostly for the aeronautic industry in system safety and reliability engineering. And since then, since 2019, we have evolved and spread all over the world. We have now a footprint covering 3 continents. And yeah, we continue with this expertise support in system safety and reliability, but we have now also a strong expertise as well in model-based system engineering and in particular model-based safety analysis. So we combine the engineering services with the development of tools, and in particular in this case you're going to see ATICA, which is our framework for safety analysis. The plan for today's presentation is first give a few highlights about how we understand digital engineering or the use of digital tools to support system engineering process. Then we will present ATICA in the large way. I mean, ATICA is a framework. We are focusing today in ATICA for Capella, which is the particular implementation of ATICA that is compatible with the Capella framework. But in the long term, we plan also to make it ATICA compatible with many other tools. And we will present the main functionalities through a use case example. In this case, we are going to present an electrical vertical takeoff and landing vehicle, one of the most, let's say, interesting or exciting prototypes that we are seeing in the aeronautic industry in the last few years. But you will see that many concepts that we are going to develop today are something that could be applied to different engineering fields and other sectors as well. And finally, we will give a brief overview of the presentation, but more importantly, we will present next steps and give you a little insights about our roadmap and yeah, the next step that we plan to do after in the coming months. So before starting, I'm going to take just 1 minute to refresh some concepts about system engineering and in particular the system engineering process represented by the V-cycle. Probably most of you are already familiar with this kind of representation, but just to refresh some concepts, we have from top to bottom the definition of a system, from the mission concept to the system and then the different subsystems that could be involved, and finally the component layer or the physical implementation layer, and from left to right the evolution of the product life cycle from, let's say, the very preliminary concept towards the end product that will be seen in the right hand side of the image. And we are going to use digital tools to support the process all over the product life cycle. So we will probably start with requirement management tools. Most of you might be familiar with DOORS or with Polarion or Jamma or other engineering tools or just Word and Excel. We are going to collect requirements, and more importantly, we want to link these requirements to architectures. And in the last few years, and of course, if you are here with Capella, you are already familiar with these frameworks. But what we will want is to link the requirements with system architectures and to develop these system architectures in the model-based system engineering tools in order to find new requirements that are applicable at lower layers of our system engineering process. At some points, the model might be so detailed that it can support simulation, and also in some cases, more advanced analysis or even code generation. In this case, we are talking about model-based design. There are specific tools for that, and sometimes it could be also interconnected with model-based system engineering. In some cases, these models are so detailed that can support what is now called digital twin, a virtual representation of the system that represents from, let's say, different points of view, the behavior of the final system that we are developing in the projects. And all these tools and methods and tasks are supported by other tools that are used to just manage interactions between the different frameworks, and in particular manage versions or control the development process of these very complex products. So our vision in Anzen is to put model-based safety analysis as an additional tool in the middle of all these ones, with the main idea of centralizing information, being able to share safety-related information across the different disciplines that we have presented just before, and being able also to make analysis as smooth as possible, in some cases even automatic, if we have let's say the correct tools and the correct source of information all interconnected. So this is the vision that we are seeing in Anzen, and this is what keeps us working all the time. We want this model-based safety analysis to be a sort of transversal tool that benefits all these engineering disciplines all over the product lifecycle. So just to present with a little bit more detail what are we talking about, I have put together this slide just with different tools that you might be using already. Of course, there is Capella, which is the main one and the one that we will be talking more about today. But our idea is that ATICA is not something that is constrained to Capella, but rather transversal and that could benefit all the different disciplines. So our vision is to develop safety extensions that allows to manage safety-related information. When I say safety, I mean safety and dependability, or safety, availability, reliability, and maintainability. Everything that is around, let's say, the correct functioning of a system and the mitigation of failures in case they occur. So we want ATICA to somehow be able to interoperate with requirement management tools in order to have a specific safety requirement libraries for complex products. We want ATICA to be compatible with model-based system engineering, and this is the main focus of today, ATICA model-based safety analysis. We want ATICA as well to be compatible with model-based design tools, and in particular, we found very interesting applications in automatic systems and systems that are capable to detect failures and reconfigure by itself. And we want ATICA, of course, to be compatible with digital twins in the future. So being able to create a framework that allows to introduce failures into very complex virtual representations of systems and evaluate contingency scenarios and response of the system against failures. But this is more like the long-term vision. Today, we are talking about ATICA model-based safety analysis, and in particular, ATICA for Capella. We have other developments ongoing. In particular, we are trying to couple with other tools that are widely used in the industry. But today, we will focus into ATICA for Capella. So after this brief presentation with the main ideas of our vision, let's jump now into ATICA for Capella, and more importantly, what does this add-on do? So in this slide, I'm going to break down the system engineering process into three main perspectives. One is requirements. The other one is model-based system engineering, which will be supported by the Arcadia methodology. And the third one is the model-based safety analysis, in this case, supported by the ATICA framework that we are developing. So it all starts with an idea of a mission, or what we call a stakeholder needs. Somebody wants a system to do something. Let's picture that we have an aircraft here. The mission is to move people from A to B or something like that. And from this need, we are going to develop different layers of analysis, starting from operational analysis, and then this will help identifying functional requirements and eventually building our system analysis with all the system architecture. These concepts are very general, and if you're familiar with Capella, of course, you already know. What we want is to have a third perspective, which is the model-based safety analysis, that is going to take information from operational analysis in order to identify under which framework this system should be certified. If you are familiar with aeronautic industry, you will easily recognize here the EASA rules, TS23 or CS25, or now in the advanced air mobility field, we are talking about the SORA analysis. So this kind of regulations that tells you which your system needs to comply to in order to be allowed to fly in specific circumstances. So it's very linked to operational analysis. It's also important to develop the system architectures. With the system architectures, we can also do the functional hazard analysis, which is going to help us identifying the severity of certain failures and to classify how our system needs to be designed and then verified in order to prove the safety of operations. Breaking down the system into more detailed, let's say, subsystems or components, we are going to find eventually our logical architectures, and we are going to have, from the model-based safety analysis perspective, the conventional analysis, so typically fault tree analysis, FMEA and FMEA. And in particular, in the aeronautic industry, we are doing this analysis following the ARP 4761 regulation. This is something that could also be tailored eventually to other frameworks, in particular automotive with their ISO regulation, or in space, the ECSS. This is something that we are looking forward to do it in the future. For now, what we are covering is the regulation of the aeronautic industry. And continue with a more detailed view of our system. We can break down the logical architectures and finish by what we call physical architecture in Arcadia, which is also called sometimes implementation. So the view that presents already the physical system. When I say physical, I mean sometimes there are physical hardware, but sometimes there is also the software part. But it represents really the implementation of the system, how the system will be built in order to meet with well, the system analysis prescription and the operational analysis that have been identified before. And here in the model-based safety analysis, since we have already detailed representation of our system and we know already which subsystems, which components are we using in the system, we can finish, let's say, our process with the reliability prediction. So this time we have not only generic function components, but physical components that have sometimes their own failure rates, and that we can propagate depending on the architectures and find the overall reliability of the system. So this layer on the right, certification, functional hazard analysis, fault tree analysis, reliability, what we want to with the model-based safety analysis framework is to have a, let's say, interconnected view or holistic view that allows us to share information from one layer to another, and more importantly, couple this information with the system information that is already covered in the Arcadia methodology, in the model-based system engineering tool. So now, how is this implemented in Capella? So we have Capella as the main tool for doing the system engineering process, and we have an extension, an add-on that brings two additional layers. One is a viewpoint, which allows to include new models into the system. You will see it just in a couple of slides, our safety meta model and the new objects that are included in this model. And then we have the safety and reliability analysis backends. This is something that runs out of Capella, but connected, which interprets the system model and propagates failures and eventually do this kind of analysis that are needed sometimes, so like fault tree analysis or Markov chains or probabilistic analysis. This is work ongoing. We are implementing this little by little, but I'm looking forward to present to you the main functionalities that we cover so far. So just to give a brief presentation of the add-on, ATICA for Capella. So for now, it's working mainly for Capella 6 and Capella 6.1. We started the development directly in Capella 6 after some feedback from different users, we saw that it was also important to cover Capella 5.2. So right now, if you try to download it, you will have the option to download the version of 5.2 or the version that covers Capella 6 and 6.1. We have not decided yet if we will continue covering both versions. We will try to merge as soon as possible. But for now, just for the users that want to have a first insight into the tool, both versions are available. We are also trying to make ATICA for Capella as compatible as possible with other add-ons. We have already successfully tested the requirement viewpoint and the document generation add-on M2Doc. So now a few words about the safety meta model and the new objects that we are introducing. So you are familiar with the Arcadia methodology, and you know already that systems can contain system functions. The new element that we are bringing is failure condition, which is an element that could be linked to a system function and that is used to describe which will be the effect in case the system function fails and what will be the severity of that failure. So this allows to classify the system functions by layers of severity, and we will see afterwards how this will be important in lower layers of the analysis. Thanks to this new object, failure condition, and the interrelationship between system function and failure condition, we are able to do the functional hazard analysis, the first one of the analysis that we want to cover with model-based safety analysis. Then, in the Arcadia methodology, system functions can be derived into logical functions, and this logical function will have also a failure representation. In this case, we call it functional failure. And it also has its own properties in order to define, well, the consequences of these failures. And again, at physical level, we are doing again the same. So we are linking a new object, failure mode, to the behavior component and also to the physical function in order to have full traceability of failures and being able to describe from the safety perspective the same way that we are doing in system engineering, so breaking down system into logical and then into physical. We will be able to break down a failure condition into multiple functional failures and eventually into multiple failure modes. So this helps us doing top-down analysis, such as the fault tree analysis. The fault tree, for those who are not familiar, is used to see which will be the effect of a failure at higher levels of our system. So for instance, we have a failure condition. We have identified that losing this system function is catastrophic. Then we will see which are the different triggers that could affect to this failure. And we can verify the probabilities of occurrence of these failures at higher level, at system function level. And we can also do functional, failure modes and effect criticality analysis, FMEA, or the summary of these failure modes, which is FMES. So this is more a bottom-up approach. We start from the component. We define the different failure modes that affect the component, and we move this element for, let's say, higher to the higher levels of logical and system in order to assess the criticality of these elements. So in order to run the model-based safety analysis, we need to start with a functional breakdown of our system, like the one you are seeing now in the slide. Just to present one functionality that I found very useful in combination with the generation of documentation is the option to create templates that generate automatic documentation from the model. We are implementing all these features because we have seen that most of our users really appreciate this possibility. So yes, we will dig a little bit deeper into this later on, but we are trying to do as much as possible, having the diagrams and then a template that allows to create the documentation directly from the different diagrams. So as I was saying, we start from the functional decomposition of the system, either in the functional breakdown or in a system architecture diagram. We create functional chains. Functional chains are important for safety point of view because it allows us to identify what will be the effect of a failure and how it will propagate through the system. And now, with our ATICA capabilities, we are able to define failure conditions. You see here on the right-hand side the failure condition element that could be linked to a system function, and then it's created automatically in the model tree, similarly to all the other elements that we have already in the Capella toolset. And then this failure condition has this dialog box that allows to bring more let's say, features and more information to the failure condition. We will see it later with a specific example, and more importantly, with a live demonstration with the Capella tool. And after we have defined a lot of these failure conditions and we have associated these failure conditions to our system functions, we can do the functional hazard analysis, which looks like this. It's a sort of table that classifies the failure conditions and summarizes the main features of this in an organized way, in a structured way. In this case, we are following exactly the prescriptions of the ARP 4761, which classifies failure condition first by the function to which it's affected here in the green box, and then defines different features such as the flight phase in which this failure condition occurs, which will be the effects of the failure condition, the severity classification, very importantly, because this is going to help setting quantitative requirements into our safety analysis, and then more other fields to describe with more detail the failure condition itself. And as I was saying before, we are always trying to be able to provide the functionality of generating documentation. So we have specific templates for this. And in combination with the M2Doc tool, we are able to generate, in this case, a word representation of the functional hazard analysis. This we will not cover today, but I want just to give you a little introduction to what's coming next. We have a plan to also implement the safety analysis at lower levels of our system analysis, and in particular physical, logical architecture and physical architecture, to be able to cover fault tree analysis and FMEA. But I will save this for later on. Let's now jump into a use case example. In this case, we are going to do just a preliminary analysis of a system, in this case, an electrical vertical takeoff and landing vehicle. So we start, as we said before, by the stakeholder needs. In this case, there is someone that wants a vehicle to be autonomous, to fly with 4 passengers, to do vertical takeoff and landing, probably because they want to operate around cities. So it's quite convenient that it can operate and take off and landing vertically. It's going to be moving around cities, and it's going to have, just to put some numerical requirements, a range and an autonomy. We need to know that there is some regulation about this kind of systems. For now, this regulation is under construction, but we have already some preliminary concept of operations that could be used as an input to develop our system analysis. So following the Arcadia methodology, we start the operational analysis by identifying the stakeholders that participate in our system, and more importantly, how our system of interest, in this case, the vehicle, is interacting with other system, and which capabilities our system provides, and more importantly, which of these capabilities need also the participation of one of the stakeholders. So I'm not going to jump into detail, but just to give a little bit, let's say, set the scene for what's coming next. So we have our system of interest, our vertical takeoff and landing vehicle. We define 2 main missions for it, the transportation of people and goods, and then, of course, ensure safety. And we break down these missions into multiple capabilities, such as emergency landing or collision avoidance for safety point of view. And for the transportation feature, we decided that we will need capabilities such as autonomous flight, communication with ground, and the vertical takeoff and landing. And we need some stakeholders involved in the loop. In this case, you see, for instance, for emergency landing, probably we need support from the police or the firefighters. Eventually, we need for the communication with ground, some ground infrastructure also that send messages to other operators of the airspace. So this all this is defined into the operational analysis, and then with more detail into system analysis. We can define a mode diagram. In this case, we represented in gray and blue the nominal modes of the system. So this system can be on ground, which is the taxi phase, can charge batteries, eventually can take off. From taking off to finding the route that is going to follow to reach destination, there is a transfer phase, which is mainly the ascent phase. Eventually, it's going to join an urban air mobility corridor, which is a sort of a street, but defined in the air. It's going to fly there for a few minutes, and then eventually will be close enough to the destination point to take again the transfer phase, and then land into destination. But there are a number of things that could go wrong during this process. And we have also some contingency modes that allow us to take control of the system and do some safety mitigation action that prevents the system to have, let's say, a catastrophic landing on ground. We break down these modes into different functions, and we assign which of these functions are active per mode. So we may have nominal functions and other functions that are only active in contingency modes. I like a lot this functional tree representation, but it's also very useful to have the system architecture blank diagram with the different functions interconnected and the functional chains defined in order to identify how information is flowing from function to function in order to provide the capability that is represented by the functional chain. So once we have reached this level, we are able now to start using ATICA for Capella, and in particular define our failure conditions. So as we have said before, we have the element failure condition here. We can drag and drop the failure condition to the system function and then start configuring the different fields that are needed in order to define this failure condition. So now I'm going to jump into the Capella framework. Now you should be seeing Capella. If you are not seeing Capella, please can somebody make a sign? But if there is no sign, I assume that you are all seeing Capella now.
No, I confirm we can see.
Thank you, Samuel. So now we see Capella. We have these the different diagrams that we have been representing. We have been talking before. So just I'm going to run a very quick new project just to show how to activate the plugin. But then we will jump. We will come back to this example and run this example with more detail. So new project. For the sake of the representation, I'm going to call it just test. I'm going to activate all the different analyses. And I'm going to pick all the viewpoints, but not ATICA. You will see after why. I want to show you how to manually activate the plugin in case you have already a model created and you just want to use ATICA in combination with the model that you have already. So now we need to go to Window, so View, Viewpoint Manager. And here in the lower part of the screen, we see ATICA model-based safety analysis. We click on our project and we reference the ATICA MBSE. Now it's referenced. So now we have we have activated the new features that are present in ATICA. The MBSE package appears here. All the different elements that we will create from now on are going to appear under MBSE package. This way is a structure in the product tree. I'm going to create a system architecture blank. Okay, now it's created. System, I can create a function. And I can create a failure condition associated to the function. This is a new feature. It's something that we are consolidating right now, but roughly you have a failure condition and a counter. This is because for convenience, sometimes we may want to see the failure condition, and when there are many, you may prefer to just see the counter. So for now, I can create multiple of them and then pick if I prefer to see only the failure conditions or only the counter or just a few of the failure conditions if needed, similarly to what we are already covering in other parts of the Capella framework. We can go one by one to the failure conditions. The screen appears. We can create a name. And we have the different boxes that allows to configure the failure condition, link it to the system function. This is automatically done because we have drag and drop the failure condition into one specific function. We can link it to modes. I'm not going to do it right now because this project is new and I don't have created any mode, but I will show you after in the vertical takeoff and landing example. And here are different features that could be assigned to the failure condition: total loss, partial loss, malfunction, the severity, assumptions, effects. All of this can be completed manually. One important aspect is that for now, these fields are, let's say, fixed. is not something that the user will be able to configure easily. We are exploring the option to define some configuration file that allows to have these fields configurable by the user. But for now, these are fixed. So after showing you the, let's say, how to activate the plugin, I'm going to jump back to our vertical takeoff and landing vehicle. So we had our system. I'm going to open the system architecture blank. So we have our system with functional chains, with multiple functions, with failure conditions associated to the function. It's not complete, but we have already a few failure conditions that have been associated to the different functions. And we can continue populating our system by putting more failure conditions into the functions. Eventually, when the system is complete enough, we can go to the system representation, system analysis, and request the functional hazard analysis. New diagram table, functional hazard analysis. It could be structured either by functions or by systems, in case we have multiple systems. In this case, I'm going to organize it by functions. I can create the new functional hazard analysis. And here it appears. We have many, many functions. It could be broke down as a tree. So I'm going to jump to these functions that are a little bit more detailed. So we have perform flight here. We have navigation functions. And inside navigation, we have, well, different functions that we defined in our example with failure conditions associated to them. We have the system component that these functions are affected to. This is in case we have multiple systems or multiple system agents in our model. In this case, there is only the system of interest. So this is why it's a little bit easier. We have a description field. We have the different modes in which this failure condition affects. This is important because, for instance, losing some particular system function might be critical or not, depending in which mode we are. It's not the same to lose, for instance, a navigation function when we are landing or when we are in cruise mode, flying at high altitude. So this is why we can configure this in different failure conditions and associate the failure condition to different modes. We have different failure types as well. It could be total loss, partial loss, malfunction. And we have fields also to describe what is happening, what will be the effect of the failure condition. And finally, we have the severity of this failure condition, which could be classified between catastrophic, hazardous, major, minor, or no safety effect, which are the classifications that recommends the IRP 4761, so the aeronautic prescriptions. I'm going to jump back to the slides. So we have presented the functional hazard analysis. Now I'm going to show you how we defined some templates that allows to export the documentation and to create a Word document with the same contents. This is something very useful because it's something that we can fully customize with using the M2Doc template and then adapt the representation to whatever process are already being used in the company or to meet specific standards in the way the documentation should be presented. So just for the final 5 minutes, I'm going to wrap up this presentation by showing you the next step of what is coming next in this framework to give you a little perspective of the new features that we are implementing and that will be ready pretty soon. So one of the main concerns that some of our partners and clients have told us is that they have already a lot of information in documents and Excel files, and they are reluctant to do the transition towards model-based. Well, in this case, we are developing specific features to being able to import this documentation and to create the same functionalities that we have seen so far, but back and forth from document to model or from model to document. This way, the work could be shared between, let's say, the conventional processes for system engineering and also the new processes supported by model-based system engineering tools. So this is an example where we imported a functional decomposition in Excel to a model, and then use this model in combination with ATICA for Capella to define the functional hazard analysis. Another feature that we are very much looking forward to implement is using the results of the functional hazard analysis to create requirements. Because once we have identified failure conditions and assigned the severity of these failure conditions, we can set quantitative requirements into the development of these system functions that are going to be inputs for the activities that come downstream. So for instance, once we have identified that a certain function is the failure of a certain function is catastrophic, we may want to implement specific verifications in order to check, for instance, that we have no single point of failure concerning the system function, or that we meet some probability requirement, some numerical probability requirement to say that this failure condition is in fact very unlikely to happen. So this is something that is going to be consolidated in the coming weeks, and that we are looking forward to implement in the next version of ATICA for Capella. And as we introduced it before, we are also trying to cover functional tree analysis, fault tree analysis, and FMEA in order to support or to provide support to engineers that are working at lower layers of the system engineering process, in particular at logical architecture and physical architecture, and to be able to verify from the models the numerical probabilities of failure and the existence of single points of failures in the system. So we are implementing specific backends to do the fault propagation. So in fact, now what we have is a model that allows to create failure modes linked to components. We can have a similar representation as the one we have seen before, but this time at physical level. And then run an analysis on the failure condition to verify if our system architecture meets the standards in order to say that our system is safe. So we are doing this through two different backends. One is cat set analysis, and another one is the fault tree analysis. So I'm going to show you just after. The cat sets look like this. There is a dialog window that allows you to configure some options, such as the mission duration or the probability threshold that from which on you consider that the failure is negligible. And it will show a report that looks this way, with the different failures and how combined trigger a failure condition at system level. So here we have in failure modes at component level. And what we have here is a failure condition on the left, a failure condition at system level. So first, we can verify that there is no single point of failure in our system because, as we see here, the order of the cat set is higher than 1. In this case, we need 2 failure modes in order to lose the function at system level. And secondly, we can also verify the probabilities of occurrence of this failure. So if we have said that the loss of thrust, this failure condition, was catastrophic, we are implementing a requirement that is probability of occurrence lower than a certain threshold. And now we can verify that the failure modes with the actual failure rates that are given by the component suppliers or by our reliability analysis, propagate these failures through the architecture in case we have, for instance, functional redundancies or physical redundancies, and finally verify if we are meeting our design criteria. The other analysis that we are trying to cover is fault tree analysis. We have already a backend that provides a fault tree analysis, but a sort of results file in the form of an XML, which is not convenient for most of engineers. So we are trying and we are developing a visual representation of this in order to meet the standards that are usually required when presenting fault tree analysis results. So just to wrap up and to give just a few highlights of today's presentation, ATICA for Capella is an add-on for safety analysis. It's specifically conceived for the aerospace industry, but we will be keen to work with other industries as well and to make it applicable to a wider set of users from different sectors. For now, our main guideline is the ARP 4761, which is the standard of the aeronautic industry. But as I said, we are looking forward to work also with automotive, with railway, with space companies in order to make it as useful as possible to a wider community of users. The framework can be tailored to meet specific use cases and company policies, in particular in what concerns document generation, as you have seen before. We have a trial version available. I invite all of you to go check our website and download it if if you are interested. For now, the trial version covers what you have seen today, up to the system analysis and functional hazard analysis. In the coming months, we will also update the CAT set capability and the FMEA. So big thanks again to the OBEO team. Big thanks to Samuel also, who helped me in the preparation. And big thanks, of course, to all of you that are connected today. I hope you like this presentation. And yeah, looking forward to having your feedback and questions. And feel free to ask.
Yes, thanks, Pablo. Thanks for those insights. Yeah, you're right. It's time for questions. Let's see that. So, okay, the first we have is from Patrice. Is it planned to integrate STPA within ATICA?
Yeah, I have to say this is a question that we are getting a lot. I'm not a specialist, but I see that there is an interest in the industry to integrate this kind of analysis. I cannot promise when it will be integrated, but for sure it's something that we need to look at because, as I said, we have this question is coming right and left. Yes, I cannot promise the date, but it's something that we will very much look forward to do it in the coming months.
Okay, thanks. Sorry. There were multiple functional decomposition levels within the system analysis level. How was it determined which function to use for the failure condition identification?
Yeah, thank you, Vincent, for this question. It was perhaps not very clear in my presentation. So in fact, here, as you mentioned, there are different layers. So we have here, let's say, a mother function, which is perform flight, and then child functions such as guide, navigate, and another child function, detect main system. In this case, what we are going to see is the failure condition associated to the function. So if we associate a failure condition to estimate position and velocity, we see it here. But if we associate a failure condition to navigation, imagine that for whatever reason, we lose the whole navigation function, it will be displayed here just under navigation. So it's something that really depends on the feature that is just under the system function. So here, in failure condition, if we link here affect functions, we chose is except of a child function, a mother function, it will appear directly under, in this case, navigate.
Pablo, you're not sharing the screen. So...
okay, sorry. Okay.
Okay, so that was my bad. The question was...
Is it working now?
Yeah, it's working.
Okay. Yeah, so I'm going to start again. So here are, as you said, Vincent, different layers of functions. So you have perform flight, then guide, navigation, control, and then some child function control, vertical ascent, descent. And there is failure condition associated in this case to this last function, and it appeared just under. If we define the failure condition at control level or at navigate level, it will appear just under the function to which it is associated. So it's something that could be customized by the user. If there is a failure condition that is somehow damaging the whole navigation function, it will appear just under navigation. Or if the failure condition is to a more specific function, it will appear just under the parent function.
Okay, next one is from Vincent 2. Have you defined a process to ensure lower levels implement compliance to fulfill system analysis probabilistic requirements?
Yes. So this is something that we are consolidating. I didn't present it today in detail. Can you share again the screen, Samuel?
Yeah, that's
okay. Cool. So here, I didn't enter into detail because it's something that we are still working on. But you see here that there is a field, failure refinement, that allows us to link failure condition to functional failure. And if I jump back to our safety meta model, which is here. Remember, a system function we can break down into logical functions and the logical function into physical function. We are doing exact same process with the failure conditions. We can break down failure conditions into functional failures and then the functional failures into failure modes. And this is what allows us to propagate failures or to link failures across different layers of architecture and to have this holistic view of our system all interconnected, and that allows then to run the automated analysis through the fault tree analysis or the FMEA.
Okay, thanks. Okay, we have a kind of variation on this question. So, are you going to support FMEA and
Yes.
STPA? But we already answered this one.
Yes. So if FMEA, you will see in the trial version that there is already an FMES, which is, let's say, a summary of the failure modes. So it allows to choose one component and to summarize the different failure modes that affect the component. The next step is to implement the FMEA. It's something that we are working on. And as for the STPA, as I said, we are having this question left and right, so it's something that we should be jumping into it as soon as possible, because clearly there is a huge need by the industry to implement this method.
Okay, and is it possible to associate a failure tolerance or a safety objective to each failure condition?
Yeah. So for now, we are classifying the failure condition into catastrophic, hazardous, major, and minor, and we plan to link this with the requirement viewpoint in order to have a sort of library of requirements, which makes that when you create a failure condition that is, for instance, catastrophic, you have automatically a requirement that says which is the, in this case, safety objective or the probability of occurrence threshold of this failure condition. For now, our classification of failures between catastrophic, hazardous, major, and minor is something that is fixed, but we are looking to different means of making something that could be customized by the user. So this way, maybe the user can create a table, create their own classification between catastrophic, hazardous, major, minor with different labels, and then associate which will be their safety objective for each of the layers.
Okay. Can you use other safety standards?
Not yet. Not yet. For now, Anzen, we started providing services for the aeronautic industry. We are specialized in this field. We have also collaborated with companies in different fields, but for now, we only cover the aeronautic standards. In the future, and if we have sufficient interest by a wide community of users, we will be looking forward to also extend the capabilities to other safety standards. But for now, we cover ARP 4761.
Okay. What is the licensing model for this tool?
Very interesting question. For now, the trial version is available for free. You can download it directly in our website. I think there is the link in the webinar. There is also the link in the Capella add-on page. Big thanks to Obeo and Capella for representing us in these websites. And if you are interested, just get in touch with us, and we can discuss specific features that you may need in your use, the way you will use the tool, so we can help implementing them. But the trial version is available for free.
Okay, and well, are you planning to provide a free license for academics?
For now, it's free for everyone. In the future, we'll see. Of course, for academic, we will have a special discount, but now it's free. So, yeah, help yourself. Okay,
let's go back to the, let's say, safety questions. Are you planning to support RAAML or risk analysis and assessment modeling language?
Okay, again, I'm not an expert in the field. What I know about RAAML is that it's more linked to SysML models. I have to dig a little bit more in the detail and see how it could be implemented into Capella. It's not something that we support right now, and I will need more time in order to answer this question.
Okay. Okay, does the tool support any kind of plausibility check and or validation for the failures and its effect? Is this what is meant by the semi-automatic safety analysis?
By the semi-automatic safety analysis, what we meant is that we can define failure modes at component level, introduce the numerical probability of these failures one by one, and then propagate across the architecture with a failure propagation model, and link to elements that are defined at higher levels of the architecture, to logical level or to system level, and verify if we are meeting the design objectives. For instance, if a failure condition is catastrophic, we may want the probability of hitting that failure condition lower than a certain threshold. This is what we meant by semi-automatic safety analysis. And about the plausibility check or validation, for now is more dependent on the engineer that is creating the model. So the failure conditions, I would say that is something that is very linked to the engineering domain. Is something that the engineer needs to have a good perspective of how the system works and which are, let's say, the feared events that could happen and what would be the severity. Then linking failure condition to failures defined at lower layers of our system is something that, of course, needs to be checked automatically by the model. So, for instance, if we have a system that implements a battery and that this battery have different failure modes, the loss of that battery, that could be something that has an effect at system level, which is a failure condition, is linked to the different failure modes of the battery. In this case, for instance, short circuit or depleted battery or things like that, that are much more linked to the hardware implementation.
Okay, and probably the last question. In the cut set analysis, which fields are to be filled manually and which are to be calculated automatically?
Okay, Samuel, do you mind sharing my screen again?
No, sure.
Okay. So, first we start with the FMES, the failure mode and effect summary. We have to fill into the model the different failure modes at component level and the probability of occurrence of this failure mode. Then we have this window to configure the analysis. The maximum cut set order is up to which level we want the calculator that is running on background to propagate failures. This is because if we want to have the full representation, it might be too time consuming, and most likely the failures that require combination of 4 or more failure modes are not really relevant probability wise for this analysis. We can configure our mission duration. This is very important because normally the failure rates at component level are normalized, and then our mission, of course, depend on the actual use case that we are studying. And we can define a threshold up to which level our failures will not longer be relevant. And then we calculate. What is happening in background is that we are introducing failure modes in all the elements of our physical representation. And using the links, the Capella, let's say, model, we have links between the physical implementation and logical and system layer. And we are using these links to propagate the failures upstream and see which combinations of failures trigger a failure condition. But this is done automatically. And finally, the report looks this way with the failure condition on the left, the different cut sets, and the failure modes that are affected to the cut set. The probability, the aggregated probability of these failure modes, and then different control fields that allows to check the result.
Okay, and we received questions in the meantime. So is there a way to link the safety rankings to functions?
Yes, so this is something that we are consolidating right now with the combination of ATICA for Capella and the requirement viewpoint. So our idea is that once we have created a failure condition and associated to a system function, automatically we create a requirement saying if the failure condition is catastrophic, probably your function development assurance level for this system function is DAL A. And this way we can automatically generate these requirements from the functional hazard analysis and speed up the process, and more importantly, ensure consistency between, let's say, the work done by the safety engineer and then the requirements that are exported to the requirements database.
Okay, and is the tool suitable to carry out system safety analysis as per ARP 4761?
Yeah. So this is the main focus of our work. Right now we support functional hazard analysis. Soon we will support also the cut sets, fault tree analysis and FMEA. And more importantly, we are developing this tool so the documentation that is generated is fully compliant with this normative standard in order to disrupt as little as possible our potential users of the tool.
Okay, thanks, Pablo. It was a very nice presentation. I tried to cover all the questions we had. I had to filter a few duplicates. If I made a mistake and you still have an unanswered question, let us know and we will forward your question to Pablo or contact him directly. But well, I hope I haven't skipped your questions. Anyway, thanks again, Pablo, for this very enlightening presentation. It was very nice work, and I'm sure you will have contacts soon about this. Let me just go back to my slides, and I just would like to recap our next events before we conclude. So our next webinar is scheduled for the 5th of October, and in this session, Eric Dano from the George Washington University will present a specific methodology aligned with ISO 15288 architecture standard to create Arcadia and Capella models. Next, if you haven't saved that yet, the Capella days will be held online from September 14th to 16th. But more importantly, if you wish to submit a talk, you only have until tomorrow to do so. So please don't delay, and we are eager to discover your use case. And finally, if you want to meet us in person, Capella will also be present in various conferences and events around the world. So I just picked a few of them, namely WSRC, and actually this is just ongoing. So I'm sure you will have the opportunity to see my colleague here, AOSEC in October, and ASEC in Liverpool in November. So feel free to drop by our boss, and we are looking to hearing from you. Thanks for attending this webinar. It was a pleasure to share this moment with you, and thanks again, Pablo. Thanks for being with us.
Thank you very much for this opportunity, and looking forward to having this feedback soon.
Have a nice day, and goodbye.